Okay, springs. Um, we've got a picture here of an uncompressed spring. Oh, and this spring is at equilibrium at this point. Then we put a mass on there, and this spring is stretched this distance x. Okay, so we've got an uncompressed spring at equilibrium. We put a mass on it, and it gives it that much stress, that much stretch. Now again, the force that's being applied here is m times g. Let's see if I can make this look more like an arrow. So m times g is the force that's being applied to this spring. Now, the stiffer the spring, means less x for the same amount of force. Every spring has its own stiffness, and if you remember last year, K is the spring constant, and it represents the stiffness. Okay, this is something that honors physics did last year. Let's move on. So, in order to determine K, if we set up a force versus displacement graph, in order to get more stretch, in order to get more displacement, we need to apply an increasing amount of force. Now, there are two things about this graph that are going to be important. The first one is the slope. The slope is force divided by displacement, and that is how you determine the spring constant. Slope is K. Well, that gives us a relationship here. Fs equals negative kx. Negative because it's, in a way, it's considered an attractive force because the spring is pulling. So the force on a spring is equal to negative k times x. Okay? The force is equal to the spring constant times the displacement. Okay, this is one that you should know. It's in your equation sheet. I'm fairly certain it's in there near the work and energy stuff. All right, then we come down here. The other thing we should look at is area. So the area of this graph is significant. Now, if we look at area, it's 1/2 f times x. Area of a triangle, right? 1/2 f times x. Well, if we substitute kx in for x, then we get, or in for f, then we get 1/2 kx times x, and of course, you could simplify that to 1/2 kx squared. So the area of this triangle is 1/2 kx squared. Well, that's significant because force times distance is the work done or the energy of the system. And so F times X is going to be work. And so Kx squared has something to do with the amount of work that's done. Let's move forward here. This is elastic potential energy. It is the energy stored in a spring. And the elastic potential, in other words, the potential energy stored in a spring, that's what the S is for, is equal to 1/2 kx squared. Okay? U sub S is equal to 1/2 kx squared. So now we have kinetic energy, 1/2 mv squared. We have potential energy, gravitational potential energy, and it is mgh. And now we have elastic energy stored in a spring, and it is 1/2 kx squared. Those are the three forms of energy we have, and in this example, we're going to do all three. So, the spring compresses 1/2 meter when a 2 kilogram mass is placed on it. How would you determine K? remember, F is equal to K times X. In this case, 2 kilograms will provide a force of, oh, I was going to put 10 newtons, but it's really 20 newtons. Remember, mg is 10 times the mass, and so 20 newtons is equal to K times 0.5. 20 divided by 0.5 is going to be 40 newtons per meter. All right, so this spring has a stiffness of 40 newtons per meter. In other words, if you apply 40 newtons of force, you will stretch this spring or compress this spring 1 meter. All right, second example, or second part of this example. The spring is now pulled down 0.25 meters and held there with the mass on it. How much elastic potential energy is stored in the spring? Now, with the mass resting on the spring, we're going to consider that at equilibrium with the mass in the system. And so by pushing it down 0.25 meters, that is your new displacement. Okay, so let's scroll down. Spring is pulled down. Now, elastic potential energy. U sub S is 1/2 kx squared, 1/2 40 times 0.25 squared. 0.25 squared is going to be 1/16th, right? 1/4, 1/16th, and so I can get rid of a few things here. 40, yeah, you guys can probably do the math on this one. So let's see, 1, 4, 10. Let's see, so it's going to be 1.25 joules. Let me actually get my calculator here. 0.5 times 40 times, where's my parentheses? 0.25 squared equals 1.25. Yay, I can do math. All right. So we have 1.25 joules of elastic potential energy. All right, let's move on to the next one. The spring is released. In other words, we're going to launch that mass up in the air. How fast is the mass going when it is launched from the spring? Now, we have that energy. And so let's just say that the stored potential energy compressed is equal to the kinetic energy released. And so if K is equal to 1/2 mv squared, I know that 1.25 joules is equal to 1/2 2 times v squared. Well, 1/2 and 2, that makes nice. And so v is equal to the square root of 1.25. Well, let's get that calculator back up here. So 1.25, where's my square root? Let's see, there it is, 1.12. So V is 1.12 meters per second. So far, so good. All right, scrolling down. Scrolling. Now, extend the page a little bit here. How high above the launch point does the mass reach before falling back down? Now, as that spring pushes up and launches the mass, it's not at 0.25 meters, it's not at 0.5 meters, it's at some other height, probably 0.75 meters, but that's assuming an ideal physics world. So we're not going to worry about at what point does the mass get released. We're looking at how far above that point does it get, which means that the stored energy, which we already know is equal to the kinetic energy on release, so compressed, released, is equal to the gravitational potential energy at the top. I think you guys are able to follow along without too much trouble. So the gravitational potential energy is equal to mgh. I believe that's how it's, yep. It's given to you as MGH in your equation packet. So 1.25 is equal to 2 times 10 times h. And then the math is going to be pretty simple here. 1.25 divided by 20, calculator, 1.25 over 20 equals 0.0625. 0.0625 meters, about 6 centimeters, give or take a little bit. Which, I mean, if you're looking at it, you know, the spring is only going to give you a little bit of speed. You know, 1.12 meters per second isn't that fast, and it'll go six and a quarter centimeters above the ground. So that's the idea. Hopefully this will give you some idea how the springs work into this. As long as you can figure out the constant, you're dealing with force, displacement, and of course energy. And so that elastic energy is going to contribute to speed and height based on the situation.